So we're going to go over your second checkpoint here, which dealt with factoring and the tray problem, as well as a couple extra graphing practice questions here. So the first four were asking you to solve the polynomials using your various techniques from lesson 4 and polynomial units on your Schoology account. So for number 1, the technique you should use here is, if you note, all three elements in the polynomial have a variable attached to it. So we can factor out the lowest degree, which in this case is x squared. Also, all the coefficients are divisible by 2. So what we could do on this first one is we're going to pull out this 2x squared, this greatest common factor between those three terms. And when we do that, it's like undoing the distributive property. We're still left with an x squared, a minus 5x, and a minus 14. So there's our first step. Now, if I look at this leftover piece, it's a quadratic, and we can factor this as normal by looking at the constant. So what factors of negative 14 add up to be negative 5? And negative 7 and positive 2 would be the pair that you would select. So here is what your factors would look like on number 1. And now the actual solutions, well, if x plus 2 is the factor, what's going to make that factor 0 would be negative 2. If x minus 7 is the factor, that means positive 7. And if it's just x, there's no plus or minus anything, that means 0 is a solution. Now note, it's x squared, which means 0 is a double root because of that squared piece. That's like an x and then another x. So there are our 4 solutions here. I know there's only 3 numbers, but the 0 counts as 2 of them, so we should always be able to find whatever our lead power is. So if it's a 4th power, that means there should be 4 zeros. Our technique on the second example would be our sneaky squares. So again, this is pretty much just like we would do with the quadratics. So what factors of 36 add up to be negative 13? And your winner here is a negative 9 and a negative 4. Now what's different here is x times x is x squared. I need x to the 4th. So it should be x squared and x squared. That's the only thing that changes here. And now same as before. If that times that is 0, now that means one of these factors is equal to 0. So there's a few ways we could approach it from here. These are both difference of perfect squares, meaning we could factor them. So what factors, because we're missing a middle term, so what factors of negative 9 add up to be 0? And our answer would be a minus 3 and a plus 3. So this is one way we could approach it. And then our solutions would be 3 and negative 3. But our other option would be just set that equal to 0 and solve it. So if I set x squared minus 4 equal to 0, I can quickly solve that. And there's our 4 solutions. So plus or minus 3 and plus or minus 2 are your solutions on number 2. On 3, this is where we're going to utilize the grouping technique. So we're going to cut that equation in pairs. And on the left side, what can I factor out of both of those terms? Well, they both have a variable, so I can pull out the lowest degree. On the right side, they're both divisible by 4. And I actually want to factor out a negative 4. And when I do that, negative 4 divided by negative 4 would be a positive 1x. And negative 12 divided by negative 4 would be a positive 3. And now as we take a look on each side, we have that common factor of x plus 3. So now that's what we can factor out of both sides. So now you can pull that x plus 3 out, and the leftover coefficients are the other factor. So the x squared and the minus 4 become the other factor. So our solutions would be negative 3. And then we already know what this is equal to because we just solved it on the problem before. So if I add the 4 and then square root it, I should get plus or minus 2. So there are your solutions for 3. Number 4, this one is our sum of perfect cubes. What that means is 8 and 125 both have a perfect cube root. So if you don't know what those are off the top of your head, remember you can use the cube root button and type it in, or you can type it as to the 1/3 power. In either case, the cube roots are 2 and 5. So if we look at our formula, we have now figured out what the A and the B are. So these are the cube root parts. So this part right here would be 2x and 5. So 2x plus 5 is this first part. Now we got to do the other part. So it's the A part squared. Well, our A part is 2x. So what is 2x quantity squared? Well, that's 2x times 2x. So 4x squared is that part, minus A times B, so 2x times 5, and then B squared, or B is 5, so 5 squared is 25. So there's the factorization of number 4. Now this first part gives us the solution -5/2. This part here we can't factor, we got to use the quadratic formula. So if we go ahead and plug them in, there is your setup. So first part is inside the root. Now here I have 4 times 4 times 25. So 4 times 25 is 100, and then 100 times the other 4 would be 400. So 100 minus 400 is a -300. And now we would use our simplification technique. So 300 breaks up into 103. And the square root of 100 is 10. So this is 10 plus or minus 10i square root of 3. All over 8. And then the 10 and the 8 are all divisible by 2. So 5 plus or minus 5i square root of 3 all over 4 would be your final reduced answer. So there is 1 through 4 solving with your factoring techniques. Number 5, you're dealing with a 12-inch by 24-inch rectangular piece, and we need to create an equation for the volume. So this is what the picture would look like for number 5, 6, 7, and 8. So we're looking at this scenario where we have this 12-inch by 24-inch piece. We're folding these pieces up on both sides the same distance to make a 3-dimensional tray. So to make the volume equation, we already know what one of them is. We already know the depth is x. The other key piece is the base. So what would we call this distance right here? Well, it was 12 totally, and then we took away an x on both sides. So we would call this dimension 12 minus 2x. The other one fits the same pattern here. It was 24, but we're taking away an x on both sides, so we're going to call that dimension 24 minus 2x. So your volume equation on number 5 would be that. You can leave it in factored form. So question 6 then was, what is the domain of this situation? So our domain is what x values are we allowed to use, and it's not unlimited here. And if you remember from the example I sent you earlier, it's between our first two zeros, and our zeros would be 0, 6, and 12. If you set 12 minus 2x equal to 0 and solved it, you would get 6. And then same thing here. If you set 24 minus 2x to 0, you would get 12. So between 0 and 6 is the domain here. Now notice I'm not using equal to signs. And this should make sense because could x be 7? Well, if we take a look over here, if I took away 7 here and 7 here, that's 14 inches. And this side is only 12, so it's impossible to take anything over 6 because it's going to make this width part negative. So there's your domain. And then 7, what was the volume if the depth is 5 inches? Now we're just going to go ahead and plug 5 into our volume equation for x. So it's 5 And then times, if you plug 5 in, you're going to get 10. So 12 minus 10 gives me the 2. And then same thing here. If I plug 5 in, I get 10. So 24 minus 10 is 14. So this is what I'm solving. 5 times 2 times 14. And I get 140 cubic inches. So the volume of the tray is 140 cubic inches if the depth we chose was 5 inches. And then the last question with the tray is, what's the best depth to give us the best volume? And this is where we just kind of guess and check. So we're going to look at values between 0 and 6. So remember, we said this graph is similar to a parabola. It's not exactly a parabola, but we can kind of use that to start our guesstimation process. So I'm going to choose when x is 3, when the depth is 3. So now it's just like 7. If x is 3, I'm just going to plug it in and see what I get for the volume. So here I get 12 minus 6, so that's 6. Here I get 24 minus 6, which is 18. So if I do the multiplication, 3 times 6 is 18. 18 times 18 is 324 cubic inches. So now I'm going to check it when it's 4. If I use a depth of 4, what do I get? So if I plug it in, I get 12 minus 8, which is 4, and 24 minus 8, which is 16. So 4 times 4 is 16. 16 times 16 is 256. So I don't have to go farther that way. The 3 is bigger, and we already know what 5 is. So now last I'm going to check is 2. If the depth is 2, what's the volume? So if we plug 2 in, 12 minus 4 is 8. And over here, 24 minus 4 would give me 20. And so 2 times 8 is 16. 16 times 20 is 320 cubic inches. So your answer for number 8 is 3. So if the depth is 3, that gives us the best volume. And the best volume we would have is the 324. So there are your 2 answers for number 8. The depth that gives us the best volume is at 3 inches. The volume we get at that is at 324 cubic inches. And the last part to your checkpoint is the graphing piece here. I know we had some problems graphing on the last one here, so I threw a couple more on here. So our first step here is we got to find the real zeros. So it's already in factored form here. So I've got an easy one here at 6. And that means it's a triple root. I've got one at 3/2, at -4, and then I have a 0 for a 0, and it's a double root. So there are my zeros. Now, these are all real numbers, so they're all going to show up on the graph. So I'm just going to plot those. So there's my 0 at 0, -4, so there's 1, 2, 3, there's -4. 3/2, that's 1.5, so between 1 and 2. And at 6, so there's 2, 3, 4, 5, and there's 6 all the way over here. So there's my 4 zeros plotted. Now you've got to find the end behavior using your lead coefficient. So this is where we're just going to multiply. So I have a -3x squared times another x. So that's -3x cubed. -6x to the 4th, and then that's times x cubed. So -6x to the 7th would be our lead term. So it's negative and it is odd because of the power. And that's negative. So that tells me what my end behavior is doing. It's going to finish going down. So remember, on an odd, the end behaviors do opposite things. So on our graph, that last 0, it's going to finish going down. And on the left, it's going to go up to the left. So there's my end behavior pieces. And now I'm going to go ahead and make my waves, noting I have a double root at 0, which means it's not going to go through. It's going to reflect off. So it's going to bounce off of this 0, and then it's going to come through the next point. Now the last one is a triple root, which flattens it out. So I could even make that line, and I could disregard this one, And it kind of illustrates the triple root a little bit better. So there's your triple root and double root into play. So the double root, it does not pass through. It hits the axis and reflects off. On the triple root, it flattens out, but it does transition from positive to negative. And number 10, same thing. So I've got -6. I've got -2. And now this last one, this is one of our special ones. So it's not a double root. The squared is not out here, meaning the factor is being squared. The squared is with the x. So this means I either have an irrational number, which means the square root's not perfect, or I have a complex or imaginary number, which means I have an I with it as the square root of something negative. So if I set that equal to 0, and I solve it, I'm going to get x squared equals 20. And when I square root it, I don't get a perfect number. So here we're just going to want the decimal approximations. Well, the square root of 25 is 5, and the square root of 16 is 4. So 20's got to be between the two. So I'm just going to call it 4.5. Now, I also want to note this 5 in the beginning. There's no variable attached to it, so it is not a 0, but it will play a role in the end behavior. So it's a little bit different than what we had on number 9, where we had this -3, but it had the x squared with it, so that made it a 0 possibility. This one, it's just a constant factored out, so this 5 could never turn to a 0 because it's a constant. There's no variable attached. So again, all 4 of these are real. Even the square root's a real number. We're just going to plot the decimal approximation. So we're at -6. -4.5, -2, and then I have a +4.5. So there's 1, 2, 3, 4, there's 5, so right in between there. And now my lead term, well, I have 5x squared, and then x squared and x squared gives me a 5x to the 4th. So that tells me my end behavior is positive and even. So it's doing the same thing, and they're both going up on both sides. So just like a parabola, any even power is going to do the same thing. And I have no multiplicities to worry about, so I'm going to go ahead and just make my little waves, and this graph looks like a little W shape. It looks something along those lines. Again, I don't care how high or low you make those humps in between the zeros. That's not what I'm looking for. I just want to make sure you have the general shape of your graphs.